Okay, yep. Okay, don't get that. Hi guys. So today I'm here to actually talk about TLS. Now, before I actually start, I just want to quickly talk about the talk we just had. Seeing something like that was actually fantastic. I've been coming to OCP now, I think 4 years. I think I've been giving talks the last 3 years. And when I started coming, it was very much, it was a hardware community. You know, we'd be talking about hardware standards, layouts of boards, that kind of thing. And I'd kind of come here and start talking about these software slides, and you know, I felt a little bit out of place. But the development within the community has actually now been amazing. You have suddenly people realizing that actually the distributed software, which fits in with this hardware, is actually really essential. And unless we start moving towards converging on that, we aren't actually going to, you know, really be able to use this stuff in the way we want to use it. So it's actually really good to see something like that. Now, as I said, what I'll be talking about normally today is TLS. But I do want to tie it into a few of the strands that have kind of been here the last couple of days. So people have been talking about chiplets, accelerator modules. There was some stuff around NIC 3.0 as well yesterday. Now, all of this stuff, as I just said, needs a software stack. So think about this really as an example of how you take these pieces and productize them up. What you actually need to get this to the point where, you know, it's something you can deploy in a large scale. So the way I'm going to go through this is just quick background on TLS. I'll try and keep it very short because I know we're running a little bit behind time. Then I'll talk really about how you kind of integrate this with the Linux kernel, which is one of the important things. And I think that's something which, as we get more and more types of accelerators, as we get more and more heterogeneous processing, you know, funky stuff, as that happens, we're going to need to really think about how we integrate that side of things. So I'm really just going to be using this as an example of how one can do that. Then just a quick intro into the NFP, which is effectively actually just a sea of chiplets. So I will go into that in a little bit more detail. And then talk about how the firmware works in this one particular example. Now, the presentation we had before went very broad. It gave different types of examples in our workloads and what the firmware really needs to be doing in those cases. I'm going to be talking about one example. There are many other types of networking loads which have very different requirements. But TLS has some unique features, especially when you are doing it in this type of environment. So for example, we had to deal with millions of connections. That needs some very specific requirements. And then finally, I'll actually talk a little bit about the benefits. You know, why are we doing all this stuff? Why are we disaggregating things? Why are we coming in with heterogeneous architectures? Why are we doing all these things? There's got to be a benefit to it. And then I will just quickly finish with the summary and call to action. So, very quick introduction. This is the TLS handshake. This happens every time you set up a connection. To actually do that requires a bunch of steps. And I'm not going to go through them in much detail today because we have 25 minutes. But what I will say is that what we're going to focus on today is the bulk encryption and authentication, which is this final step here. Now, the importance of that depends on your use case. If you are running large amounts of machine-to-machine traffic, and you're running cases like streaming, and you know that's, for example, I mean, I think Hans had a slide yesterday in his presentation where he showed the amount of machine-to-machine traffic versus the amount of user-to-machine traffic that you have. The vast majority is machine-to-machine traffic. Those types of cases, this is the important part, because you're keeping the connections open. Now, the converse is, if you are a multi-tenant data center and you have zero control over anything that's going on in your systems, actually you end up tearing down and pulling up a huge amount of connections. Then the first part becomes your bottleneck. So we're going to focus on the type where the second part is in fact the bottleneck. TLS record, sorry, this is just very, very quick basics, just in case people aren't up to speed. TLS is a record-based protocol. You have these giant 16K records, which are the maximum size you can have. You've got a very small header, which is 5 bytes. There's actually in TLS 1.2, there's an 8-byte nonce, but let's not go there. And then if you, at the end, you have a 16-byte authentication tag. That authentication tag is where the sort of encryption and authentication part comes in. Because obviously you need to make sure that if you have encrypted data, you've got to make sure that the encrypted data actually gets to the other end correctly, because you have no real other way of actually checking that, because it's encrypted. Just another quick point on here is that TLS is, I put always in brackets there, because people are looking at standards around using QUIC with effectively TLS. It's slightly different, but there's a few things like that which are coming through. But in effect, TLS is always over TCP. TLS is designed to be handled in order. Now that's important, because what we have as a processor, and you'll see, is effectively a sea of cores. So if you do an out-of-order run-to-completion model, which is kind of what we would do in many other circumstances, that doesn't really work when you have to handle the first packet before you handle the second packet before you handle the third packet. So there's a few key things in there. Now, the exact implementation details, though, are slightly cipher dependent. With AES GCM, you have, which is the sort of main cipher used in most use cases, you do have a bit of flexibility, because of the fact that the actual encryption is really independent between 16-byte blocks. So it's on a 16-byte block basis that the encryption itself is done. And the encryption is relatively independent. There's an incrementing counter between the blocks, but the actual authentication is the part which actually requires the entire thing to be rolled up. So the authentication tag, the thing I pointed out, that's 16 bytes at the end, that really needs to be done serially. There's a few bits of magic you can do to kind of do 8 16-byte blocks, that kind of thing at a time. And if you actually go and look at the kernel code for the CPUs, for the Intel CPUs, you'll see that they do 8 blocks at a time. That's why the 256-bit instructions is quite important for them. Okay, so that's kind of TLS 101. What I'm going to talk about next here is I'm going to talk about the actual kernel architecture. How does this work within the kernel? So this is at 50,000 feet. If anybody who knew this code was here, they would probably run at me and throw bricks at me. So I'm gonna be very, very nice and say that this is very high level. Effectively, what happens is you've got an application. The application writes to a socket. That's just a chunk of data there at the moment. Then what happens is the TLS upper layer protocol, which is implemented by the kernel, will pull the data and it will recordize it. It's not really a word, but I'm going to use it. And what it does is it basically puts it into record-sized chunks. So this can be 16 kilobytes or smaller. And it adds in the 16-byte authentication tag at the end. Now, this is not the correct authentication tag yet. This is just some random data which the kernel has grabbed from somewhere. Actually, that's what it used to be. It's actually slightly changed now. They're doing it in a slightly safer way now. And then that gets sent off to the encryption stack in the kernel, gets encrypted, gets authenticated, put into records which are now encrypted, and then it will get split up into packets via the TCP stack and just get handled like every other piece of traffic you have in your network. So why is this architecture important? So this is something which I think Dave Watson's the guy who did this a few years ago. And the reason he architected it like this was to design something which you can then actually start doing some offload on. And what does it look like when you do the offload? So remember I said the offload, we're really just doing the bulk encryption and authentication. That's what we're offloading. We're not offloading the framing section either. The framing itself is still done in the kernel. So that piece of the framing where it takes the data, puts it into records, adds a 16-byte chunk at the end, that is still all done in exactly the same way it was done before. However, now it just doesn't encrypt it or authenticate it. It just sends that data as still as plain text through to the NIC, and the NIC does then the encryption and authentication on the way out as the data is transmitted. So this is how you effectively offload it. And the reason why this architecture was important, and it took a while to design, is because one of the key things in the kernel is that you obviously can't go and corrupt the TCP stack. The TCP stack needs to be aware of what's going on when you're running TCP. Otherwise, you end up with some pretty scary potential bugs. So this is one of the key design features when we were doing this, is to make sure that you keep the TCP stack doing what it does. And that's why you need to add in the 16 byte to the top there as well. That's why you need to do that first, because otherwise your sequence numbers and all that is going to get out of order, and then your streams are going to be slightly confused. This is the receive path. So the receive path is very similar. The same principle applies. You don't want to change anything through the TCP stack. The TCP stack sees exactly the same amount of bytes as it would anyway. And what then happens is that the actual records, which are still encrypted with their authentication tags. I see I've made a little error here. The authentication tags have somehow made it to the top of the records here. That's a little bit of a bug. What happens here is that those are placed inside, effectively, the socket, waiting to be read. The socket will then read it, and it's only when the actual call to read the data comes in that it then will go and decrypt it, and then pop off the authentication tags and send it on to the application. So that only happens actually at socket read time. And again, from this model, you can see that this model makes it pretty easy to offload to the hardware, because then all you do is you do the decryption in this case, and you also do the authentication checking at the NIC level before packets come through. Now, this is important because this is one of the more difficult things you'll have to do in these cases. Is as the NIC, you are actually having to keep track of some layer 4 networking state here, because you've got to make sure the packets are coming in the right order. If the packets come in the wrong order, you've got missing packets, your TLS stream is not going to work. You're not going to be able to put things together and make that work. And that's quite important, because that leads to resyncs. So I haven't covered in this talk, because I'm keeping it very short and I don't want to get into too much detail here. I haven't covered the control ABI for this or resyncs. These are kinds of the exception cases. This is actually where the hairy details come into it. But the reason why I've spoken, for probably 10 minutes about the kernel stack in a hardware presentation is because when you start getting things to the point of trying to productize it, this is what you're going to have to do. You're going to have to integrate with this stuff, because otherwise we're going to have a very tough time controlling all this heterogeneous hardware. And it kind of, with the experiences we've had in this sort of space, one of the most important things we've kind of learned is to, reduce, reuse, recycle. What we tend to find is that if you can find interfaces which are out there already, which can serve some of your purposes, that's very important. So, for example, one of the things to look at in this sort of heterogeneous world we're moving into is there's a concept in the kernel called switch dev, which effectively allows you to control multiple ports and systems which are much more complex. So being able to do that with the kernel is actually going to be, I think, something we're going to probably have to look at in the coming years. But we can talk about that in a year or two. Okay, now moving on to the hardware. So that's great. We've now got an architecture which gets things down to the hardware. We can do encryption, decryption, authentication in the hardware. But what does that hardware look like, and how does that change the way we have to design our firmware, which is the other important piece of the software in this case. So very quickly, this is what our chip looks like. Effectively, each one of these is actually a timing enclosed chip. So you've got a huge sea of small processors, which are all hooked together. Inside here, you can obviously see that you've got a significant kind of blocks, which are sort of larger logical blocks. Now, this is kind of effectively, Bappy might kill me if I say this, but this is effectively in many ways a bunch of chiplets all hooked together on a bus. We have a bus called the DSF CPP bus, which this all hooks into. But you could easily imagine using something like AIB or a bunch of wires to connect up what is effectively a large Mac block here to the actual flow processing cores, to things like the crypto engines over here. So actually disaggregating that is almost the way our software already has to think about it. Our software already thinks about these things as different chunks of stuff. So that is actually something which I think is going to be important as time goes by. One of the key things about the architecture which we've had to take into account for the TLS case is, for TLS, we need to be able to handle millions of connections per NIC. Now, bear in mind, this is a 20-watt little NIC, and this thing is having to handle over 2 million connections at a time. Now, you can't keep that in SRAM if you are running at 20 watts. We have to have DRAM attached. What is the problem with DRAM? DRAM is slow. Now, luckily with TLS, you are looking at bulk transfer, really. Your latency is less important unless you are running a smaller amount of smaller connections, in which case there's some caching structures and stuff which I don't go into, which can significantly reduce issues like latency there. But what we have in terms of a memory architecture is we have this huge multi-threaded beast. So what we have is each one of the cores actually has 8 threads. The memories themselves all have multiple threads as well. This is the cluster target memory, which is the small memory which sits actually locally to the sea of cores. But there are larger DRAM controllers, and there's actually, I think, don't quote me on this, I think there are 16 threads per DRAM controller times 16, so there's 128 threads running per DRAM controller. There are 3 of those. So you've got a huge amount of memory operations which can actually be in flight all at the same time, and can be either loosely ordered or strongly ordered, depending on how you want to look at it. So this piece is crucial in this case. This is not important if you are doing something which is latency sensitive and tightly coupled. This is important when you are doing huge amounts of TLS connections all at the same time. And the other part of this is the crypto cores. So the crypto, this is probably the highest level diagram I think I've ever drawn about these things. But anyway, the crypto cores are effectively a small processor in and of themselves. They have their own instruction set. They are fed actually by cores which are locally. You can see we've actually got a few cores here which are locally to the crypto cores. Now those guys are actually feeding instructions to the crypto cores. So they're actually feeding it into their pipeline. So these are actually different types of processors which are independent, all working together and actually feeding each other instructions. That's all great. Now I'm going to show you the most complicated diagram I think you'll probably see in the next 2 days. I apologize for this, but I think it's the only way to really explain it. So this is a day in the life of a packet. This will be, I promise this is as deep as it's going to go. What happens when we have a packet come in? You have the packets come in, we handle them in an out of order fashion in that large sea of cores. Then after we've finished with that, so actually what happens is the sea of cores have a set of macros running inside each one of these cores. And if we are running crypto, there's a specific set which run, but there are other macros to do other things if you have other tasks running, and you can switch them in and out. So effectively what happens is they get handled by the large sea of cores. That does a lookup in a session table. And this is important because at this point we have, I think we probably have about 600 threads running. So we have 600 threads running in parallel here, which are doing all the lookups to the session table. The session table is where all of the encryption data for each one of these connections is sitting. And if you have a huge amount of connections, you need to do that in parallel because you need to hide that latency. So that's why having a huge amount of threads for this particular use case is extremely important. Now, I said this is out of order. We then need to get them to those crypto blocks. The crypto blocks have to handle things in order because, as we said earlier, TLS is an in-order protocol. Now, luckily, what we do is, because we've done all the lookups here, we effectively are able to put the state basically tied to the packet. So we have all of the crypto information we need to be able to decrypt that particular packet of that particular flow in the back of the packet. So all of the information that's relevant will actually now be put into here. We do a small cam lookup because there's a small chance that that state has changed in the time that we've gone from here to here. So to do that, we need to actually do a small cam lookup on a little cache that we have locally there. Then if there's been any changes, we have to do a lookup there, but that effectively doesn't go all the way back to the session table. That actually goes to a small cache, which is local. And then we actually do the encryption processing with the instructions that are also tied to the back of the packet. So we actually take the instructions and move the instructions around with the data. And then finally, we do what we call a recirculation, which is that we put it back into the out-of-order cores to do any final cleanup. These are things like cleanup checksums, any other small pieces of work like that that need to be done. And then once that's done, we send them out to reorder and send them out onto the wire in order. Now, the reverse happens obviously when you're going in the other direction, but that gives you an idea. Now, if you actually want to go look at this stuff, we have now open sourced our firmware. So we've put this up. The initial version is on GitHub. This does not include all of the crypto code, but it does include the basic instruction passes. It does include the basic data path. You can find this. I've got a link at the end in the call to action. And I think that that's really going to become an important part. I mean, if, what Bape was talking about yesterday around ODSA is that, we're now at the point where people need putting software on top of this stuff. The only way we're going to get good software is if it's open and if people are able to look at it. So this is kind of just being a little bit of a Hail Mary to just see whether we can get people involved on that side. So we've already actually had a couple of contributions from people who are our customers who wanted to change things slightly. So that's actually been a very useful little thing, and I hope that's the direction which the world goes in, because the only way we're going to get really good software for all these weird and wonderful architectures we're going to have is that if people can share and compare. So finally, just to finish off, because I realized that we started very late, but I don't want to take up more time and make things even later. So very quickly, why are we doing this? A couple of very, very, very quick benchmarks. So this is the test which was done. Effectively, we had an application called LowGen, which, excuse me, I've had a little bit of a sling malfunction. We had an application called LowGen and an application called Thrift Server. Now, these are all both open source applications as well. They were actually done by Facebook. You can find them on the Facebook GitHub. Those are available, and you can actually run this exact same test if you want. And these are the benefits we saw. So these are the percent of CPU cores. Now 100% is one core. Obviously, we've got a many core system here. And if we could compare what happens when we run with software TLS versus hardware TLS and plain text, you can see that obviously the plain text and the hardware TLS are very close to one another. Now, the important thing is the use case here. So this is with very large records. If you are running with much smaller records, the framing, which was the first section of the work, the bit that doesn't get offloaded, is more of the work. So it depends on your use case, and it depends on the size of your packets. Not packets, records. Because if you have much smaller records, then you are going to require much more record processing to actually frame things and put the authentication tags on, because you're going to be doing it more often. So a word of caution, make sure that you understand your use case before you go any further. Finally, just putting it all together. So TLS offload gives us a nice example of something you can do on a OCP v2 NIC using an accelerator, which is effectively a sea of chiplets. So it's kind of, I think, something which is very similar to things we're going to see more of as time goes by over the next little while. As we get more accelerators, as we get more of this type of heterogeneous processing, we're going to see more of these types of use cases. And we're going to have to tightly couple them with the software. And finally, just a call to action. So we've got a new MEZ v2 Type 5 spec. This is available. I don't think it's finished yet. I think there's still a couple of iterations to go, but it's going to be there soon. This effectively has allowed us to put expand the MEZ V2 in the vertical direction, because we're going to put a slightly larger heatsink on that. So that allows us to be able to pack in more programmability, and if we want to potentially up the frequency of what we're dealing with. We obviously have a link to the card and the design, and that's kind of where we stand. So finally, the call to action here is we've got the open firmware. Obviously, NetDev, if you're dealing with the kernel stuff, that's where that happens. We've also actually got OpenNFP, which is a Netrunner-specific group which deals with our processors. So if you actually go and take our firmware, poke at it, find some issues, just complain on there, and somebody will talk to you, hopefully. And finally, obviously, OCP MEZ. That's where the work has been going on for the slightly new form factor MEZ V2 NIC. So I think that's basically everything I have. Thank you guys for listening. That was a lot of information in a short period of time. So if you need to poke me, come and grab me anytime and ask me any questions. Yeah. Okay, thank you.
Can I ask you a question?
Sure.
So it's offloading the crypto for TLS onto
Yep.
the disk. What's the value of putting it there rather than putting it in a different accelerator?
Yes, so putting a sideband accelerator in.
And then my other question
Yep.
is, does it affect the overall security?
Yep.
Because,
So yeah, so there's
you can be more susceptible
Yep.
to like a most
there's two advantages versus sideband accelerators. The first one is there are some cases actually where the sideband accelerator adds a bit more latency. There's a second issue with the sideband accelerators where the way that this comes back again to the architecture. The software architecture for the sideband accelerators has a couple of things which needs to be worked out still. And there's a bunch of guys, I think at NXP actually, who've been doing a lot of work on this. So I think they're going to keep working on it, and they're going to get there. But it's probably needs a couple more iterations before we really get to the end of it. But there are cases where one is better and the other is better. If you are doing stuff locally, like for example, if you decide you've got to go and use your accelerator to encrypt a bunch of stuff which you're going to plonk onto a disk as well, then you want a sideband accelerator. However, if you are dealing with a network-heavy use case, then the network side makes a bit more sense. Because of also all the stuff around the sequence numbers, and if you get resyncs or you get dropped packets with the sideband accelerators, the stuff I didn't talk about, that causes some fun edge cases there too. So it's horses for courses. The second question was the security one. So around that, I think it's very important if you go down this path, you've got to have signed firmware. So this is some of the trusted firmware stuff, which actually I think I'm not going to say which group it's in, but there is some work going on within OCP around trusted firmware, around signed firmwares. You've got to have a root of trust within your system to be able to do all this stuff. Now, that's definitely not what I was talking about today, but all that stuff is super important. Otherwise, none of this makes any sense to do. Completely correct. Hey.
So, yeah, a lot of information here. One of the challenges in the offload is the control plane and all the exception cases.
Yep.
Especially TCP retransmission packets.
Yes. Yes.
Losing the record boundaries. And so
Yes.
TLS offload, quite familiar with that. How do you address those and get it integrated with TCP stack?
Yeah. So I decidiously, that's not the right word, but I definitely avoided those. So there are two ways that we do the resyncs for this work. The resyncs is the key issue you run into, and that's when you get retransmissions, that's when you get missing packets. The first is one that works, is a very lightweight method, which works well with RPC type traffic. That is effectively where you have, actually I've got some backup slides maybe on this.
I think we need to get going.
Okay, yep, I'll go very quickly then. So you have one version where you just guess the next record boundary. If that fails, then you guess 2 in the future, then you guess 4 in the future, and you go on like that, and usually you'll catch up very quickly with RPC traffic because it's connection-based, which is the key advantage you have. If it's streaming, you need to do more predictive work, and there's a bit more complexity there, and we can talk about that one offline. Yep, sorry.